Okay, so let us start, right? So vector calculus, today is the introductory part. So in vector calculus, whatever the syllabus, whatever we have, in the vector calculus, right? First, let me list down the entire syllabus of UPSC. So this syllabus contains scalar and vector fields, and the second one is differentiation of vector field, differentiation vector fields, of a scalar variable. And then gradient divergence, and then curl, in Cartesian and cylindrical coordinates, Cartesian and cylindrical coordinates, higher order derivatives, vector identities, and vector equations, application to geometry, that is curves in space, curvature and torsion, Serret and Freinet formulae, curvature and torsion, Serret and Freinet formulae, Gauss and Stokes and Green's identity, Gauss divergence theorem, Stokes theorem, and Green's identity. This is the part of the syllabus, right? So in this syllabus, whatever we have discussed, right? So there are certain parts of this particular syllabus where UPSC is going to stress. So those parts are, so mainly two sections. One is Serret and Freinet formulae, so here actually there are two parts. One is so this one, applications to geometry, in this Serret and Freinet formulae. So curves in space, curvature, torsion, this one Serret-Frenet formula here. So this section is going to be stressed more. This is one section where you can expect questions, because in the entire vector calculus topic, so this is the part actually where you feel a little bit confused. So that's why actually UPS is going to stress more on this. This is one section where you can expect the questions, and another section of this particular syllabus where you can expect questions for UPSC is, that is the Gauss divergence theorem and Stokes theorem and Green's identity. So this is another place where you can expect questions. So because actually the proof of this particular theorems, proof of theorems meaning verifying Gauss divergence theorem for a certain surface, verifying Stokes theorem for a certain contour. So such kind of things actually he is going to ask. So these are the two sections where you can expect the questions from this particular area. Other than that, the applications, that is scalar and vector fields. So this actually you need to understand what is a scalar and a vector field, and then the applications of this scalar and vector fields with the help of this three-dimensional vector identity called del. So these things actually, if you apply on different fields, that is if you apply on a scalar field del phi, where phi is equal to a function of x comma y comma z, then you are going to get the gradient. Now gradient, how you are going to interpret the gradient, and then how you are able to identify a normal vector of a surface with the help of gradient, and how you are making use of that gradient as part of divergence theorem, all those things actually are going to be tested. So here actually this entire first part of the syllabus is necessary to understand the second part of the syllabus, but the questions are asked from the second part of the syllabus. Got it? Understood or not? So that's why actually, so if you wanted to learn this one, you have to be aware of all these things. So, and then this vector calculus is one topic which is very, very important topic, especially from the fact that, so this is very much gross level it is going to be used in case of fluid dynamics. So that's one particular area, so where you will be rigorously using this entire part of the syllabus. That's the reason. So this is going to be tested indirectly even at the stage of fluid dynamics. So that's why you have to be very clear here what you are going to learn it here. The same applications or the calculation of, so actually in fluid dynamics, if you wanted to prove the continuity equation where del dot D is equal to 0. So this is nothing but in a fluid dynamics. So this is what is the continuity equation. Based on this continuity equation, so he is going to ask the questions. Now the fundamental methodology of proving the Gauss divergence theorem is going to be asked as part of the fluid dynamics, indirectly asking to prove del dot D is equal to 0 for different kinds of surfaces. There the problem is, with the help of Cartesian coordinates you might be very familiar with, but with the help of the cylindrical coordinates and the spherical coordinates, where you are going to be tested. So that's why most of the people are pretty comfortable with the Cartesian coordinates, but what he is going to ask is the spherical and cylindrical coordinates. So that also you have to be aware of it. Got it? So that's why there are two sections where you are getting confused. That is, if you change the coordinate system to polar, or if you change the coordinate system to cylindrical or spherical, you are going to confuse. That is one section. And another is, so when analyzing the space curves, that is space lines or the space curves, if you are going to analyze it, so there is something called Serret-Frenet formula. So this entire section will be discussed. So this entire section, application to geometry, is discussed as one particular unit, but it covers all the aspects like finding out the curvature, finding out the torsion, and Serret-Frenet formula, how it is going to be related. So each and other. So all these things part of the same syllabus or the same unit, but so the stress is more on this because there is very lot of confusion on this particular topic. Got it? So that's the reason actually this section actually you have to be carefully understanding. So other than that, nothing great about it. So this is one of the very easiest topic, but the base understanding of this, which you have to be aware already, right? So that is, you have to be aware of the coordinate systems. So that is a must. So coordinate system is a fundamental topic for almost every topic. So that you have to be very aware. So cylindrical coordinates, spherical coordinates, and Cartesian coordinates, and the relations between these coordinate systems, you have to be aware of it. That is one important aspect before covering this particular topic. And then given a equation, you should be able to trace out the surface. So that is very much needed. So usually if you are pretty comfortable with the multiple integrals, So that will be straight away useful at this particular stage. Got it? So these are the fundamental topics that are part of this syllabus. Got it? So the questions expect from here only. But this is the fundamentals what you need as part of understanding this particular topics. Got it? So any questions on this? Any questions on this? Right? No. Okay. So to understand this topic, right? So the assumption here it is you are already aware of vectors. So that is the base understanding, especially three-dimensional vector. So that three-dimensional vector understanding you should be pretty clear, not the two-dimensional vector. Usually in physics what you are going to learn is two-dimensional vectors usually. So in mathematics actually if you study +2 standard, there actually vectors is a big topic where it covers all the aspects of it. So if you are comfortable with +2 topic of vectors in mathematics, then actually that syllabus is sufficient enough to understand any part of this particular syllabus. So here vector calculus actually it will test both the understanding of the calculus, at the same time the understanding of the vectors. Together it will form the vector calculus, which will give a beautiful application to engineering. Got it? So nowadays most of the research whatever is happening is based on the vector calculus, mostly the vector calculus. So most advanced research will be dealt with only the vector calculus. So why? Because so if you know, so Maxwell's equations, if you notice, so the Maxwell's equations are purely derived from the mathematical understanding of vector calculus, which changed the complete physics. So that is purely based on the mathematics. So he proved that actually, so Maxwell proved that light is a wave, so and it is an electromagnetic wave. So if you are able to combine the electric field and the magnetic field together, it is going to propagate in a wave phenomena. That was purely proved from the fact of vector calculus. And then nowadays actually the most advanced research is dealt with only the, so this one Maxwell's equations. So the wave optics, quantum mechanics, so this one is part of this vector calculus itself. Got it? So that's the great level of understanding of vector calculus. But the concepts are pretty clear and easily understandable. Only thing is you should be able to imagine the space or the curve in a 3D. That's the only difficulty part of it. So you have to be aware of that fact. Clear? Okay. Any questions on this? Any questions? Okay. So books to start with vector calculus, B.S. Gravel Higher Engineering Mathematics is one of the good book. So you can start with that, and he explained very clearly and easily, right? So that book is sufficient enough for vector calculus. Mostly, almost every aspect actually it was covered. Got it? In that particular book, Higher Engineering Mathematics by B.S. Gravel. Okay. So you can expect 50 marks minimum from this particular topic. So accordingly, you plan for that. Yeah. So now actually first we will start with a scalar field and a vector field. So a scalar field is nothing but a field which is simply contains the function of, that is x comma y comma z. And one more important aspect I would like to notice is, that is, so this vector calculus plays a very, very critical role in the engineering or the physics only when there is fields comes into picture. So first of all, you need to understand what is a field. So a field is nothing but, so it is having influence at every place. So that's what we call as the field. Suppose if you take the example of gravitational field. Gravitational field means if I leave this particular chalk piece, it is going to hit the ground. Now the same chalk piece, if I move to Bangalore and then drop it, there also it is going to hit. Suppose if I move to Allahabad and then drop it, there also it is going to hit. So everywhere actually it is having the same effect. So such effect is called as the field. Got it or not? So such effect is called as the field. Here actually nothing you can view there. So wherever if I leave it, so it is going and touching the ground. That means there is a straight line you can draw from there. So that's what is called as the field line. So there is an imaginary line. So if there is an imaginary line, so really it is not present. You are imagining there is a straight line like this. So if I leave this particular chalk piece, it is going to go in that particular straight line format. So that's what we call as the field. Everywhere it is there. So wherever the field is there, then we are going to deal with the vector calculus. Here, what is a scalar field and what is a vector field? A scalar field actually, which is simply a function of the position x comma y comma z, is called a scalar field. Now, this is associated with certain value. So, for example, so this is scalar. Actually, let us say I call potential. Potential is a scalar field. It is a scalar field. So why we call this a scalar field is, if I take this particular chalk piece to this height, it is get certain potential energy. So this potential energy, whatever it is going to assume, so this is dependent on only one fact, that how far it is high from the ground. That is the only factor it influences, right? So that means the position of this particular chalk piece is directly related to the potential energy of this particular particle, right? So this is what we call as the potential energy. So potential energy is a scalar field. It depends on only the position. Now, so this is what we call a field which is dependent only on the position and assumes its value based on the is called scalar, a scalar field. And then the other part of this is, so this is a scalar field. The vector field is nothing but, so the direction is also matters there. Now a vector field, for example, if I take the electric field, if I take the fluid field, so these are the vector fields, not the scalar fields. So gravitational field is a scalar field, you can take it, because everywhere it is a straight line, it is going in a single manner. But actually, if I take electric field, here actually, suppose if I want to move charge from this line to this way I wanted to move it. Now, under the influence of an electric field like this, so this electrical field is dependent on the direction also. So in certain directions it is going up, in certain directions it is going down. Now, depending upon the direction of this particular field, so my movement charge, right, is dependent on it. So here the field is not a scalar anymore. So this field is nothing but a vector field. So vector field, so this is a vector field. Usually, for example, a fluid field. Fluid field we mean, suppose if the fluid is moving, so fluid will move if there is a difference in energy, right? Obviously, if there is a flow, that means each and every particle of the fluid is going in one or the other way. So there is a direction associated to each and every particle. So that is given by grossly, it's the velocity of the fluid. Now every particle is having certain velocity, maybe more or maybe less, but it is having its own direction. Now everywhere it is associated with its position, but in a directional manner. That's what we call as the vector field. So usually a vector field is represented as F is equal to phi of x comma y comma z into I. So here the directional component comes into picture, plus psi of x comma y comma z. So it is dependent on the position, and at the same time it is dependent on the direction as well. So this is j cap, and then plus and the gamma of or delta of x comma y comma z into k. So here actually if you notice, this is a vector field. Here there are three different scalars and each is associated with one or the other direction. Now this entire field together we call as a vector field. So a vector field whose magnitude whose value is dependent on the position and the direction is called a vector field. Right? So this is the understanding you should be having it. So a vector field will contain this ijk, at the same time it is a variable. So it depends on the position. And a scalar field is just dependent on only the position. So direction is independent of it. So phi of x comma y comma z, there are no I, j, k components which are nothing but the directional components. Here there are I, j, k components. So these components actually you have to be aware of it. So this is a vector field, this is a scalar field. Got it? Any questions on this? Got it? Okay, so do you have any questions? No, great. So then actually, so there is something called a del, so which is an operator that comes into picture as part of this vector calculus. So this del operator is defined as I dou by dou x plus j dou by dou y plus k dou by dou z. So this is termed as del. So del actually it's an operator. And this is a vector operator. So a vector operator, we mean this can be treated as a vector. So all the vector properties of cross product and dot product is applicable here, right? So this is a vector. Now it can be operated on a scalar as well. For example, del phi, if I take it, so phi is a function of x comma y comma z. Now this is operated on I dou by dou x plus j dou by dou y plus k dou by dou z operated on the function phi. So this is I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. So this is a scalar became a vector now, right? So to convert a scalar to a vector, then this is how actually you are going to put it. So this is what we call as, so del phi is called as gradient. Now here this gradient, what it is doing for us, see this, if you notice dou phi by dou x, this is nothing but the variation in the direction of x. So the functional change in the value of phi in the direction of x, the functional change in the value of phi in the direction of y, the functional change in the value of phi in the direction of z. So all these three together is turned as a single vector called del phi. And then the operation what we have performed here we call as the gradient. Got it? Exactly in the similar manner, this can be operated onto the vectors as well. So this is del phi if you wanted to operate. So this is a scalar multiplication that is done, which is nothing but operated onto the vector is giving us the gradient value. Now vector operator, suppose if I have del dot d, where d is a, or del dot f, where f is phi I plus psi j plus xi k. So where phi, psi, j are the functions of x comma y comma z. Now if it is operated as a dot product, then this is going to be I dou by dou x plus j dou by dou y plus k dou by dou z dot phi I plus psi j plus xi k. So now if you do the dot product, this is going to be dou phi by dou x plus dou phi by dou y plus dou psi by plus dou xi by dou z. So this is the operation del dot f, right? So this is del dot f. So here actually you have operated this vector operator onto a vector. here we have operated a vector operator on a scalar. Now here the vector operation, once it is done, the scalar became a vector component now. Here the vector, that is del dot f, both are vectors. The result what we are getting is the scalar. Got it? So this is the vector operator. You can operate on a scalar or vector. So the dot product will always result into a scalar. So that's why you got this one. What is the utility of del and gradient, right? So this gradient actually a three-dimensional derivative. So three-dimensional derivative, right? So it is going to give the effect on all the directions together. So each direction the function value is changing. For example, if you imagine a surface which is a kind of this kind of surface like this. Now the change there is in x direction there is a change, and y direction it is a change, and z direction also there is a change. Now this functional change, how it is going to be operated along x direction, y direction and z direction. It is nothing but the derivative or nothing but the slope value in different directions separately it was calculated here. Now this gradient is having a beautiful application in finding out the surface integrals. So where you are expected to find out the normal vector. So the unit normal vector you have to associate with the surface. So this normal vector you will be able to find out with the help of del phi, where phi of x comma y comma z equal to c is the surface represented by this particular surface. Now for this actually you need to calculate this del phi, and del phi by mod del phi. So this is going to be the unit vector in the direction of the normal to the surface, and this is useful for us in proving the Gauss divergence theorem, or when we apply the Gauss divergence theorem, this is the key role, so which plays there. Now the application of Gauss divergence theorem is very vast in electric fields and in the fluid fields, wherever it is. So in the application of fields, the Gauss divergence theorem actually plays very critical role. For that you should be using this del phi value to find out the normal vector. Got it or not? Right? So it has got its own importance actually. Every part of this particular vector calculus has got its own importance to a greater extent. So maybe like actually some are directly useful like Stokes theorem. So Navier-Stokes equation is one of the important topic as part of fluid dynamics. That's what we have discussed, right? So Navier-Stokes theorem is directly is nothing but the Stokes theorem what we learn as part of vector calculus here. And then Gauss divergence theorem, whatever we are using it, so whatever we are learning in vector calculus, in electric fields, right? So it is going to be straight away used there. And then the same Gauss divergence theorem we have used as part of fluid dynamics as continuity equation, which plays very critical role as part of UPSC syllabus there. So there also the divergence theorem del dot d we have calculated there, right? And then Gauss divergence theorem. So one is directly using as the continuity equation, at the same time proving the amount of quantity that is accumulated at one particular place is getting calculated with the help of divergence theorem only, right? So all those things are the multiple applications. So here actually for that you need to be calculating the gradient. So gradient is a three-dimensional derivative. If you want to find out the directional derivative or actually in one particular direction, what is the change of the function that is happening? If you are asking, then the directional derivative you have to calculate. That can be done only with the help of gradient. Got it? So all these things are the applications of the gradient, divergence and curl. So the next aspect is the curl. Curl is nothing but del cross F. So this can be operated only on the vectors, right? Del can be operated only on the vector. Sorry, del cross F is nothing but a vector product. So here two different vectors operated with a cross product is going to result into a vector. Now this vector, so the vector you are going to get it. Now this curl is nothing but the rotational component of the field. What we mean here, see this, suppose there is a field that is present, then the field can have an effect on a particle either to move in a linear direction or to move in some curved fashion, right? Suppose if the water is moving like this, then here, from here to here, this is a linear motion that is going there, right? Now from here to here, this is no more a linear motion. So there is some kind of curve that is coming in the movement of the particle. Now till this point, so you can straight away say that because there is a potential difference between these two are moving from here to here. And then here actually it's no more moving in linear. So there is some linear component, there is some curved component. Now this curved component, how much it is going to be? So this is what is calculated with the help of this del cross F. So del cross F is nothing but the rotational component of the fluid or the rotational component of any particular field. So the effect on a particle because of the field, is it going in a straight line manner or is it going in a curved fashion? So if it is a curved fashion, then del cross F is no more zero value. If it is going in a straight line manner, there is no rotational component. In this particular range of fluid flow, this is del cross F value is equal to 0 because there is no curved fashion. For the particle, whatever it is here, so this is straight away moving from here to here, but this is not taking a curved path, right? So in this particular case, del cross F is equal to 0. This has got very, very great application. Right? I told you. So I just explained. So if del cross F is non-zero, then there is a rotational component. If del cross F is non-zero, then there is going to be a rotational component of the fluid particle. That means, suppose if the water is moving like this, then the fluid particle which is present here, this is going to take a curved path like this. If it is taking curved path, then we say del cross F is not equal to 0. Then the methodology of analysis of the fluid, here it is completely different, here it is completely different. So in our fluid dynamics, there are two different chapters altogether, and the questions are expected from only those two topics. Those topics are, one is, so this is the potential flow. So this is the potential flow area. So from here to here, the flow is because of only the potential difference. If there is a potential difference, there is a flow of the fluid here. And then from here to here, this is no more a potential flow. So this is a curved path, right? So if it is a curved path, then here del cross F is not equal to 0. Then if del cross F is not equal to 0, you cannot use the methodology of the potential flow to solve the problems at this particular place. So here there is something called vortex flow that comes into picture. Vortex. So this vortex flow is completely different and the potential flow is completely different. Now this is one of the very, very important aspects that changed our engineering to a greater extent. That is, so in electrical engineering, if you notice, there is something called potential that is going to be defined. That is nothing but, so the work done in moving a particle or the charge from one place to another place in the presence of electric field, we define as the potential there. That potential concept comes into picture only from the fact of vector calculus, where this del cross F, if it is equal to 0, del cross F, this is equal to 0, then F can be expressed as del phi. So this is a vector identity. Del cross del phi is equal to 0. So if this is the case, if this is coming out to be 0, then these two are actually parallel, obviously, del cross of del F, del phi. Now, if it is 0, then F can be expressed as del phi. So this is one of the very, very important fact which changed our methodology. That is, this is a scalar value. So this is a scalar value and F is a vector. So it gives the ideology of converting a scalar to the vector. So we need to be operating only with the help of vectors, but it is very, very complex for the analysis purpose. If you take an electric field, it is a vector field. That vector field is having its own direction. Now when you want to calculate the vector field effect because of multiple charges, let us say 100 different charges are present. So each field, so each charge is having its own impact in a particular direction, right? Now every charge is having effect at one particular point in one or the other direction. Now if you consider as the vectors everywhere, then handling 100 different vectors in 100 different manners is very, very complex. So almost impossible to do that. But if you are able to convert that into a scalar, then you can straight away add it. So without having much of difficulty, because addition of scalars is straightforward. Suppose if this chalk piece weight is 100 grams, if I have one more chalk piece which is having 200 grams, the sum is straight away we can say that 300 grams. But if I have a force of 10 newtons in one direction and 20 newtons in another direction, so the addition of these two together is not equal to 30. So that makes all the difference. So if it is not equal to 30, then what next? So that is going to be the vector addition, which makes our analysis completely complicated. So there, the concept of the potential simplified being a scalar. So this scalar you are able to define only if you notice this del cross F is equal to 0, where there is no curly flow, where there is no rotational component of the flow. So here is the place where there is no rotational component. So that is why this part actually you can define a scalar which will define the potential between these 2 points. So there is a proverb in English, that is, water always flows from top to bottom, because there is a potential difference between these two. So that is the analysis what we are going to adapt it here. It will be a straightforward linear motion. So this flow is called as the potential flow. So that's why in the fluid dynamics our analysis will be completely divided into where del cross F is equal to 0, where del cross F not equal to 0. If del cross F is equal to 0, then we say that is a potential flow. So that potential flow is simplified with the help of defining this del phi, where phi is a scalar value. This is the potential. So this potential value, it just depends only on the position of the particle, right? Not the direction of the particle. So if the position is at this particular point, if the position is at this particular point, and these 2 points are having a potential difference, then the particle is subjected to move from here to here. So that is the methodology we are adapting. But here in this case, so it's not because of the potential. So because there is a curl. So that means this simplified methodology is not applicable at this particular point. So that's why you have to define a complex potential here. So that complex potential so will be much more difficult, which you need to adapt for the analysis of the flow where there are curls, that is del cross F not equal to 0. Got it? So this methodology is the vortex flow. Clear? Got it? So these are the some of the important aspects actually. So I have just introduced the aspects. So these are going to be used as part of vector calculus to solve the higher level of problems. At the same time, the applications of this vector calculus to the fluid dynamics is very much applicable. So those things actually you have to be very much understanding at this stage itself. Clear? Any questions on this? Repeat. So I just repeated, right, everything. See this. So scalar value. So here actually you are defining a scalar. So this simplified our flow. This part only you are asking, right? So yeah. So del phi. So this del phi actually phi plays very critical role in simplifying our mathematical analysis in case of fluid dynamics, right? In case of vector fields anywhere, in case of gravitational field or any field you take it, the simplified methodology can be adopted if there is a linear motion. That is, if there is a straight line motion, then for the particle, then you can adopt this del cross F equal to 0. That means F can be defined as del phi. So this actually, in case of dipoles, in chemistry, dipoles, or actually in physics, when we deal with the dipoles, we are going to adopt the same principle. That is, we calculate the phi value first, because that is easy to calculate, and then add it up together, the effect of both the charges there, and then apply del on this to get the value of the electric field, right? Even if you take the magnetic dipole also, exactly you can do with the help of the same analysis. So this is applicable where del cross F is equal to 0. That means the particle movement under the influence of the field is straight line. But here in this case, if it is not under the straight line, then there will be a curved flow. So if there is a curved flow, so this is what we call as curl. So del cross is nothing but curl, means rotational component. So if there is a rotational component, then this is no more a potential flow. Obviously, it won't flow in a straight line manner. Got it? So this has to be exactly analyzed in a much more complicated way. So where you have to deal with the vectors, no other way. Yeah, obviously, right? So Deepak, you said correctly. So that is, if there is a force field which will move only in the linear direction, so that is the curl 0. That's exactly the reason we have defined potential energy as part of the particles moving high. So you might have noticed that. So suppose if I lift this chalk piece, this has got certain potential energy. How? Because so here actually the movement is linear only. Whatever may be the direction you take it, the effect it is going to move only in the straight line fashion, wherever you stand there. Got it or not? So here, is there any curly flow? No. So if there is no curly flow, obviously there is no curl. Hence, we simply take the potential energy straight away without even understanding this del cross F. At 10th or intermediate standard itself, you might have calculated the potential energy simply without knowing any vectors. So here actually, the vector calculus is the base to understand that. So here actually, if there is a linear direction only, the effect is showing in the linear direction only, then there is no rotational component. Then del cross F is definitely 0 for gravitational field. Hence, in a gravitational field, F can be expressed as del phi, where this phi is the potential energy for us, which is equal to mgh if you move the particle to a height of h. Got it or not, Deepak? Any other questions? Okay, so that's all for today. So in the next class, actually, I'll start with the gradient, and then so let us see how it goes. Fine. So that's all for today. Thank you. Good night.